Special methods start and end with double underscores. Python community also calls them dunder methods or magic methods. These are some examples of special methods. Among these, you have already seen the usage of dunderinit. Dunderinit is used to initialize an object. This method gets called automatically when an object is created. Like dunderinit, you don't have to call these special methods directly. There will be some top-level function or syntax that will call these special methods. These special methods are Python's approach to allowing classes to define their behavior to language operators. You will see a common pattern once we look into the details of a couple of these special methods. You should never use this naming standard for your methods or attributes. They are reserved for Python. Even if you write a dunder method with a custom name that doesn't clash with Python's current special methods, it may happen in a future version of Python. The special methods are documented under the Data Model section in Python language reference. Consider this simple class for representing a person. We are creating a new object of this class. When we type the variable name and press enter on the Python interpreter, it shows the representation of that object. The current value shows the class from which the object was created, and the memory address at which the object is stored. This isn't very useful. Next, let's try adding the dunderiper method to the class. The arguments that a special method should accept, and the values it should return, are specified in the data model documentation. The dunderiper method shouldn't accept any additional argument. It should return a string. Now, if you try creating an object, you will see its representation has changed to the string value we return from the dunderiper method. Python has a built-in function called reper. When you pass an object to this built-in function, it calls the dunderiper method of the object. The Python interpreter uses this in interactive mode to show the representation of the objects. There is another very similar special method called dunderstr. This is used by str and print functions, as well as various formatting functions. Using our previous example, the default representation remains the same in all cases. Next, let's try implementing the dunderstr method. This method also shouldn't accept any extra arguments, and it should return a string. In our case, I'm returning the name attribute. If we create an object from this class, the representation still shows the default value. But if you try printing the object, or call str on it, they internally call the dunderstr and return the name attribute. The format strings also use the dunderstr method to get the string representation of an object. Now you might be wondering, the dunderstr and dunderiper look similar in syntax and functionality, why do we need two, isn't one of them enough? The difference is in their purpose. The dunderiper output is typically for the developer. It's more useful for debugging. If possible, try to make it look like a valid Python expression that could be used to recreate an object, as we did in our example. This method gets called when using the built-in reper function. The dunderstr is typically used for display purposes to an end user. It's usually a nicely printable string representation of an object. In our example, we were using the name attribute for this. It's used by str, built-in functions like format and print. You will see this pattern in many places. For example, take a look at the datetime library. The representation of the date object is different from its string value. If dunderstr is not implemented, but dunderiper exists, Python will use that instead. The dunderlen method is used to retrieve the length of an object. This method is called by the built-in function len. It should return an integer greater than or equal to 0. Usually, your class will be using the built-in list to store some data and you return the length of that inner list. Every object in Python has an associated truth value. For any non-zero number, the truth value is true. For 0, it is false. In the case of collection data types like lists or dictionaries, the truth value of an empty collection is false, and is true otherwise. By default, any custom object also has a truth value. It is always true. You can override this by defining the dunder-bool method. It must always return true or false. In the next example, we are writing a class representing a rectangle. We would like the Boolean value of the rectangle objects to be false if both length and breadth are 0 and true otherwise. If dunder-bool is not defined, Python looks for the dunder-len method. If dunder-len returns 0, then the object's Boolean value is false. Otherwise, its Boolean value is true. If your class is for representing a collection, you can implement the dunder-len method and skip implementing the dunder-bool method. Then the behavior of your class will be consistent with other collection types like lists or dictionaries in the standard library. Similar to what you saw till now, Python also allows you to define how your objects respond to arithmetic operators. I will be just showing dunder-add in this video, the rest all follows the same pattern. If you understand one of them, you should be able to read the documentation and implement other arithmetic operators when needed. Consider this simple class to represent a point. If you create two instances and try to add them using the plus operator, you will get a type error, saying unsupported operands. Next, let's try adding an implementation for dunder-add. I'm also implementing dunder-str to get a readable representation. The dunder-add method accepts what's on the right side of the plus operator. We first check whether that is an instance of the point class itself. If it is, we add them together by adding the x and y coordinates of each point. An important thing to note here is that we are not modifying the existing point object. We are returning a new point object. If the other object is not an object of the point class, we are not raising an exception. Instead, we return not implemented. For arithmetic operators, you may either not implement the corresponding dunder method at all, or implement and return not implemented. Let's say, we also want support adding a point object and tuple object. Currently, that won't work. The implementation is easy, we simply add a new check to see if the other object is a tuple with length 2, and add the elements. The problem is that, even though you can only have the tuple object on the right side of the plus operator. When the tuple is on the left side of the plus operator, Python calls the tuples dunder-add method and passes the point object to it. The tuple class is unaware of our point object and doesn't know how to perform addition with our point object. This is where the reflected operators come in. When Python tries to add a and b, Python is calling the dunder-add method of the first object a, and passing the second object b to it. If this returns not implemented, and the operands a and b are not of the same type, then Python will swap the operands and try calling dunder-add method of second object b, passing object a to it. Let's try implementing dunder-reflected-add for our class. The implementation is the same as that of the dunder-add. Now, it's possible to have a tuple on either side of the plus operator. Since we already implemented addition with a tuple in the body of dunder add, we could simplify the dunder reflected add method. A corresponding reflected method exists for all of the arithmetic operators and they all follow the same pattern. The arithmetic operators that we discussed so far always return a new object. Python also supports augmented arithmetic assignment operators. These methods should attempt to do the operation in place and return the result. An example of this is how the plus equals operator works for lists. Notice that the operation didn't create a new list, but modified the list in place. Not all objects are mutable, for example, integers. They cannot be modified in place, only a new object can be created and assigned back to the same variable. A simple example is shown here. In our custom class, we use Python's built-in list to store items. Here also I'm implementing the dunder reper to display the contents of the inner list. Notice that in the implementation of a dunder I add, we are mutating the inner list and returning self. As expected, if we create an instance of our custom class, and add another list to it, our object is modified in place, no new object is created. If the special method corresponding to an augmented arithmetic assignment operator is not defined, Python falls back to the normal methods. This means if x and y are two objects and if we do x plus equals y, Python first looks if x implements the dunder I add method. If not, the normal dunder add implementation of x is used. If that also doesn't exist, Python looks for dunder I add of y. Next, we will look into Python's rich comparison operators. These are operators like less than or equal to, and so on. Their implementation is similar to arithmetic operators. In this example, we are implementing the less than operator. Our implementation only supports comparing with another value object. If it's not an instance of the value class, we return not implemented. As expected, the comparison works when the object on the right side is another value object. When we compare our value object with an integer, we get an exception. We could provide support for comparing with any real numbers by creating an instance of our value class from that real number. Here, we first check if the other object is a real number. If it is, we reassign the other variable to a new instance of the value class. The rest of the code remains the same. Now we can check if a value object is less than any other real number. Now also, the real number cannot be on the left side of the less than operator. However, it is possible to check if the real number is greater than the value object. This is possible because less than is the reflection of the greater than operator. So, when you do a less than b, Python first calls the dunder lt method of a and passes b to it. If that method returns not implemented, Python will swap the objects and call dunder greater than method of b and pass a to it. Similarly, greater than or equal to is the reflection for less than or equal to and not equal to are each other's reflections. Usually, you don't need to provide implementations for all operators. For example, assume our value class implements less than and equal to operators. Then the implementation for less than or equal to can be provided using those. Similarly, all other operators can be derived from those two operators. This can be done using the total ordering decorator provided by the functools module. Your class only needs to provide an implementation for dunder eq and any one of less than, greater than, or less than or equal to operators. Implementation for the rest of the operators will be derived from them. You don't even need to implement dunder eq for total ordering to work. However, if you don't provide an implementation for dunder eq, the default implementation for equality check is using the ID of the objects. This might not be what you want. So, it is better to implement dunder EQ by yourself. For an object to be usable in a mapping type, like as a key in a dictionary or as an element of a set, it must be hashable. This can be implemented using the dunder hash method. By default, if we don't provide an implementation for dunder hash, Python derives a hash value from the ID of the object. The equality operation is done by comparing the ID of the objects. So the hash of each of the objects of your class will be different even if they have the same inner attributes. If you want to treat two such objects of your class with the same attributes to be treated as the same object when used as a key in a dictionary or as an element in a set, you need to override the default dunder hash and dunder EQ methods. If two objects are equal, then they should have the same hash. Here, we provide an implementation for the dunder EQ method for our class. An interesting behavior is that, when you provide a custom dunder EQ method for your class, the objects of your class are no longer hashable. So they cannot be used as a key in a dictionary. If two objects are equal, then they should have the same hash. That is why we need to implement the dunder hash method ourselves. Here, we use a hash of the tuple combining both name and age attributes. Now the objects of our class are hashable and thus they can be used as a key in a dictionary. Next, let's take a look at the purpose of the dunder call method. When you implement the dunder call method on your class, the instances of your class become callable. This means you can call the instances of your class just like a function, passing arguments to it. You might be aware of the partial function in the standard library. The partial function allows us to create a new function from an existing function with fixed values for a few of the arguments. In this example, our function accepts 3 arguments. We are creating a new function with 1 and 2 as values for the first 2 arguments of our function. When we call our new function, we only need to pass 1 argument, which becomes the 3rd argument for our original function. This code snippet is a rough implementation of the partial function in the standard library. This is taken directly from the documentation. The partial function takes a function as its first argument, and then any number of positional and keyword arguments. These become the values that are fixed on every function call. The slash is to indicate that the first parameter, func, can only be passed as a positional argument and not as a keyword argument. Inside the body of the partial function, a new function is defined which also accepts any number of positional and keyword arguments. Then a new dictionary called new keywords is created by merging the keyword arguments from the partial function's definition and that of the current function's definition. Then the actual function is called passing all these values and the result is returned. The original function, positional arguments, and keyword arguments are set as attributes on this inner function object. Since Python is dynamic, you can set attributes on almost any object. These attributes are useful for inspection from the user's side. Let's try implementing our own partial function. Within the dunder_init method, we will set the function, positional, and keyword arguments on our instances just like how the original partial function does. Then within the dunder call method, we merge both the keyword arguments, execute the actual function, and return the result. Using a class and implementing dunder call method is useful when you want some code to be executed before or after the actual function call and want to save some state. For example, when implementing decorators. In some cases, using a class might be more readable than defining a function inside a function. You don't have to remember the specifics of each special method. Just remember the pattern. For every top-level language function or syntax, there will be some associated special methods. For example, the len method calls the dunder len method of the object, the plus operator calls the dunder add method, the function or method call syntax uses the dunder call method of the object and so on. Whenever you want the instances of your class to behave in a certain way to language operators, look in the data model documentation of Python for the corresponding special methods.